to this computer.
Hey, good
Okay.
morning, Professor. How are you?
Yeah, fine. How are you doing?
I'm fine. Thank you for asking.
Okay. It's April 16, 2025, Physics 7. We're recording it now, and I am correcting. Let me get my notes. Oh, let's start with the syllabus first, right? Here you go. Am I sharing my screen? Not yet, right? Go. Here you go. We are writing here on the 16th of April. We will continue with induction. We're almost over with induction. And we will finish today, and then we're going to do lab number 4, single resistor circuit. Okay, and let me get my notes. Right here. I need the other notes. Third page break, April 16, 25, Wednesday, and week number. Week number 10. Week number 10. Meeting number. What's the meeting number here? Meeting number 16. So let's see. I started correcting lab report number 2, and I should have it done before the end of the day. You'll be able to see your grade, and I will upload also the correction sheet, okay? I should finish correcting them today before the end of the day. Okay? And what I want to do, yeah, let's not forget. It's always good to remind you, right? Exam is going to be next Wednesday, 7 days from now, from 8:40. From 8:40? No, it's not 8:40. It's 9:40. Here you go. Gotta fix that. 9:40 to 11:40. Here you go. 9:40, right? To 11:40. 9:40 to 11:40. And that should be version. Let's see if I upload version 11. I'm going to stop sharing momentarily. Yeah, okay, so here you go. So that'll be version 12 now. And gotta go back, sharing the screen. Okay, that's the one. Version 12 here. Okay, right? It's 940 here. That was the mistake that I had here was the mistake that I carry over from the previous semester, previous time that I taught this course. And okay, we are going to have another holiday very soon after the exam, Genocide Remembrance Day, right? And okay. Okay, so what I want to do, I want to repeat what I did last time. I want to repeat what I did the last time about self-induction and mutual induction. I found out a better way of explaining that to you, and it's going to be easier to understand. Okay, self-induction and mutual induction are the magnetic counterpart of the capacitance and resistance. That's that's a very good way of defining self-induction and mutual induction. Okay. Now, what's the difference between self-induction and mutual induction? What is the difference between self-induction and mutual induction, right? That's the question that you have to put to ask yourself. Okay. So capacitance is a parameter related to a capacitor. Capacitance is how you, let me write that down too. Capacitance is the, let's say, quantitative capacitance is the quantitative parameter of a capacitor. That's how we quantify a capacitor, okay? Capacitor, that is how we quantify a capacitor. The same for inductance, the same for resistance. You go. Resistance is the quantitative parameter of a resistor. That's how you quantify a resistor. And let's see, inductance, right? Self-inductance, and mutual inductance are the quantitative parameters of an inductor, which is one of the basic devices in electricity and electronics, are the quantitative parameters of a inductor. And that's how we quantify an inductor. And by inductor, which is, by the way, a magnetic device. The device that uses the magnetic field. And it's a very important device. It's used to build radios, for instance. Without an inductor, you cannot build a radio. It's used to, your cell phone has inductors there. In your circuitry, okay? And then the next question is, what's the difference between self-induction and mutual induction, okay? The difference is very simple. Self-induction is a parameter associated with very important, single inductor, okay? If you have just a single inductor, that inductor, and when I mean by inductor, I mean, a coil through which a current passes, okay, passes. The simples of all inductor is the solenoid. The simples of all inductors is the solenoid. The simples of all inductors is the solenoid. Okay? So self-inductance is a parameter associated with a single inductor. And then mutual inductance, here you go, mutual induction is a parameter associated with two or more inductors, okay? Two coils next to each other. Okay, that's why I showed you that illustration of one coil inside another one. Let's go back to that illustration. Magnetic field, electromagnetic induction, right in here. Do you remember that you saw that video about a magnet being inserted into an inductor, into a coil, right? The coil is the inductor. Okay, so that magnet is inducing a current in that coil that has no power whatsoever. Now, here you go. Right in here. Okay. Now, look at this other inductor here. This other inductor has a power source right in here. This power source is a generator. It's a generator that makes current flies move back and forth into this wire, right? At a given instant of time, the current is flowing in this direction. A little bit later, the current is going to flow in the other direction, and then going to keep on moving, repeating this oscillating pattern of motion of the current. It's possible to create something like that with a generator. And the generator is something that we find there at the power company, the electric power company. And they send that power to us through the transmission lines. If you plug a device to measure the current and the voltage in the outlet of your house, and if the device is sensitive enough, you'll be able to see that that voltage is varying between 110 and minus 110 volts. 110 and minus 110 volts. Depending on the resistor that you're going to get there, you are going to connect to the power outline, to the power, to the wall, right? The current is also going to vary like the voltage. And that depends on the resistor that you connect. So let's write that down here. Okay, here you go. Okay, consider now a solenoid connected to a generator, okay? Like the power outlet at home. The power outlet at home is connected to a generator very far away from us, okay? And this generator produces this AC current. So a generator, okay? Voltage and current are going to vary sinusoidally with time. Sinusoidally. Yeah, okay, looks like with time, okay? Because now there's one more important situation here. Because the current is varying in time, comma, it will also produce a magnetic field that varies in time inside the solenoid. Picture that, okay? Picture that. So if I were to if I were to depict it here, let's see here. I'm gonna play a movie with this guy, okay? Let's see if I have already something here to help me out, save time, to help me save time. Let's see. Yeah, it looks like I will have to do it from scratch. Oh, maybe it's in the other one. Let's see. It's gonna help me save time, big time here. Previous one. I'm going to draw the magnetic field lines inside the solenoid. That's the idea. Okay. Yeah, it looks like I have to, what a shame. Oh yeah, here you go. I have it. What I want. Okay, so I'm gonna copy all that stuff. Let me see if I have a better drawing. Yeah, I'm gonna have a better drawing here. Here you go. I'm gonna copy this one right here. Those are the lines of magnetic field inside my solenoid group. I'm gonna group those guys and I'm gonna shrink it so it can fit there inside my solenoid. So inside my solenoid, I'm going to have this magnetic field lines. Ah, that's terrible, right? I'll have to remove let me remove the line, the wires here. Otherwise it's gonna make you feel dizzy. It's making me dizzy, by the way. I'm removing those lines that depict current just for the sake of not becoming dizzy. Okay, here you go. But don't forget, we do have here you go. That's what we see inside. Oh, what's going on here? And what's that? Yeah, okay, good. Okay. Well, if the magnetic field is pointing from the left to the right, it means if we use the right-hand rule, it means that the direction of current in this wire here is going to be something like that, just by using the right-hand rule. Just by using the right-hand rule. Here you go. Like that. Huh? Right? Here you go. I'm going to use this guy here. Here you go. Direction of the current. Here's the direction of the current at this specific instant of time. Okay? At this specific instant of time, the current is flowing in this direction. Okay? As time goes by, the current is changing, right? As time goes by, the current changes in intensity, and then that's what's going to happen to your magnetic field as well. Your magnetic field is going to change its intensity. And I'm going to do it in a different way now. Let's see here. So I can give you the illusion of a variation in the intensity of the magnetic field. Here you go. I'm going to shrink this guy. See that? I'm going to do the same with this one. Group it and shrink it. Right? Even better, I'm going to copy this one and paste on the top of this to make sure that I have the right like that. Here you go. Magnetic field inside is shrinking, so is the current as well, right? The magnetic field depends on the current. I gotta do the same here for this other guy. But I want it to be lined up with this. Elizabeth Castellano, here we go. And I'm gonna do here the same as this one here. And then it's just a matter of repeating what I did for the other intensities. Not just repeating, but also, here you go. A given instant of time is like that. A little bit later on is going to be like that, smaller, smaller, right? Is smaller. Can you picture that? That's the best way that we can, the best way to visualize a magnetic field is by those arrows. So let's see how it's looking like, right? So here you go. Magnetic field larger, the smaller. Oops, didn't get smaller. What happened here? Oh yeah, got it. Okay, got it. Yeah. And then I gotta shrink this other one as well, right? Otherwise, the field is not gonna be uniform there. We can go for another one here. Here you go, even smaller. It's gonna be almost zero. In this case, it's gonna be almost zero. Okay? So here you go. Almost zero. Almost zero. The current too is almost zero here. I can shrink my current. And next time, the current, the magnetic field and the current, they are going to invert the direction. Okay, let's do that. I'm going to invert the direction of the magnetic field. This is a very good way of visualizing what happens to those invisible quantities. Let's see this one here. Yeah, this one here. See that? Pointing to the left now. Format shape. And this one should be zero. Here you go. One more. Oops. Imagine doing all that stuff by hand, right? Thanks God we have computers nowadays. Okay, so here you go. And now my current has a reverted direction as well. This one here, I'm gonna group it, switch it direction, just like the other one. Okay. The thumb, right, points in the direction of the current. The thumb of the right hand points in the direction of the current, and the palm of the hand points in the direction of the magnetic field. Okay? Points in the direction of the magnetic field. And then the next step, here you go. Are you getting the, this one here is repeated. I gotta remove this one here. Okay, so here you go. One, the smaller, the smaller, the smaller, revert direction, right? And now what I'm gonna do, I'm gonna copy this one here, paste right in here, and just change their direction. Okay, so here you go. Let's play the movie again, you know, little by little, right? Here you go. Remember, well, we are supposed to have those wires wrapped around the cylinder, right? But just because it looks so, you know, odd when we look at something like that, you know, I decided to remove those wires around the solenoids. Okay, so here you go. Magnetic field in decreasing, 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 changing direction. And now the magnitude is going to increase. The magnitude is going to increase. This one, the next one is going to be this one right in here. Okay, and invert their direction. Okay, and then let's see, 1, 2, 3, 1, 2, 3, and then we have 4. 4 right in here. Okay, here you go. Let's see if I can, yeah, I think I can do it. Good. Okay, so here you go. That's the picture that you must have in your mind. Magnetic field is decreasing, decreasing, decreasing until it changes the direction, and then it starts increasing again, right? And then it's going to change direction again. Then it's going to change direction again. Not going to change direction. It's going to decrease in magnitude. Now, here you go. Let's do the full cycle, right? We're going to do the full cycle here. Another one. 1, 2, 3, 1, 2, 3. Here you go. 1, 2, 3. I'm going to copy all the stuff here. Decrease. Let's see. Losing track of my movie. Here you go. Decreasing, 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 change direction. Okay, I gotta change the direction here as well. This one should have the direction changed, right? And now it should be increasing. Okay, reached maximum value. Now it should decrease again. Okay, oops. I don't need that. I need, okay, I need this one right in here. Okay, and I need this one. I need this one, right? Let's see if we have the full cycle now. Decreasing, 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 changing direction. Increasing, increasing, increasing. Decreasing, decreasing, decrease. Oops. Now I should have another one here. This one that I should have here. Before you change direction, right? So here you go. Decreasing, 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 change direction, increasing, 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 decreasing, 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 change direction, right? And then gonna increase again. And now we have a full cycle. Now we have a full cycle. Going back to what we had before. Okay? That's the peak that you have to have of the magnetic field. Okay? So here you go. Let's write that down. Okay, because the current is varying in time, it also produces a B field that varies in time inside the solenoid. You know, see recording, right? Video recording. See video recording. See video recording. Now there is one more thing, very important. Because the B field inside the solenoid is changing in time, comma, it will also induce I'm gonna call it a self, it also induce a current, induce a current on itself, okay? That is called self-induction. So not only a change in magnetic field of the solenoid can result in a current induction in a second solenoid, but it also can self-induct another current in itself, okay? Okay, and this phenomenon of the induction, this phenomenon of induction can be quantify it. Just in terms of what we call inductance. Call inductance or self-inductance in this case, okay? In this case, it would be self-inductance. And how do we quantify that? Well, we quantify by that formula that I mentioned to you before, right? And I'm going to do the derivation again. Here you go. I updated my notes, and I'm going to copy that. And at this point, no, it's not this one, is it? It's the other one. It's this one right in here. Here you go. The inductance can be obtained from the relation between the induced voltage, right? And the change in magnetic flux. So here you go. Oh, not here. For capacitance, we have this relation here. Charge over capacitance. The voltage is charge over capacitance, right? Which can be here written in terms of the delta Q over delta T with the deltas, delta raised to the 0 power. That's a very nice way of mnemonic way of memorizing the how the whole thing evolves for all those three different devices. The capacitance being the capacitor being the simplest device of all. Next, for the resistance, right? This V equal Ri, where I can be written down in terms of delta Q over delta T. And let's not forget this operator delta over delta T is raised to the first power. Okay? And now, evolving even further, we can get from Faraday's law. Here you go. Here. This is Faraday's law here. Here's Faraday's law. P here stands for the primary inductor. The primary inductor is inducing a current on itself. Okay? Is delta phi over delta T, the flux, right? The magnetic flux over delta T. This magnetic flux can be here written in terms of a current, okay? Of course, magnetic flux can be written first in terms of the magnetic field and the area of the inductor. And on the top of that, this magnetic field can be written down in terms of a current. That's what I have writing here. For the solenoid, the magnetic field is given by this relation, right? Where this N here is the number of turns per length. Mu naught is that constant that you already know. And this I here is the current that changes in time. This parameter doesn't change in time. This parameter doesn't change in time. And for our specific example, the area of the solenoid doesn't change in time either. For this reason, everything that is independent of the time can be taken out of the delta I over delta T over delta, can be taken out from inside this parenthesis, right? Can be taken out from this operator. And then we get this relationship here, okay? And now, what is the self-inductance? The self-inductance is exactly this parameter that you see right in here. That's dependent on the geometry of the device, okay? And that's what we call the inductance, okay? The inductance, by the way, is represented by the letter L. And let's not forget, I'm gonna go another step here. Let me put here L here first, and then here you go. L is the symbol for inductance. And let's not forget that this term here can be further here written in terms of the charge, right? Here you go. But yeah, here you go. Which, by the way, ends up being written in a simpler format, like that. Here you go. This whole thing I'm gonna call the L. whole thing I'm gonna call L. And here I call delta square, delta T square. And now I don't need, okay, anything else. Here is the term of self-induction. Okay. Now, what about the mutual inductance? Mutual inductance is a little bit different. Okay, it's a little bit different. It's a little bit more complicated too, because now you're going to have a second inductor inside a secondary inductor inside this primary inductor. Okay. So let's go illustrate that. But first, let's play the movie again, right? So you can have a clear picture of what happens. I didn't notice that I didn't. You're going to see that the current here, I didn't adjust the current, right? Maybe you should do that. Here you go. Decreasing, decreasing. See, I gotta decrease that. So you have everything nicely. Okay, decrease, and now change direction, increasing. Opa, I gotta get this one and paste here. Oh, you know, I also have to get this one here, right? Let's make it everything correct, right? Go. And I have to shrink this current a little bit more. Copy and paste. Shrink it even more. Hey, wait a minute. Increasing. Oh, well, it's increasing. It's not decreasing. Yeah, I decreased it. So let's increase it now, right? One more, increase even more. Right? And I gotta get rid of that. Gonna yeah, we're spending too much time with that. Let me just finish that. And here you go, increasing. Okay. And now what I want to show you, I want to show you what happens in this configuration. When we have a configuration like that, then we have this other parameter called the mutual inductance. Okay? When we have a configuration like that, one solenoid inside another one, we have this other parameter that we call the mutual inductance. So that's the difference between self-inductance and mutual inductance. What about mutual inductance? Mutual inductance is a parameter that occurs whenever we have one inductor inside the secondary inductor, right? One inductor, the secondary one, inside the primary one. Okay? The primary one. In this case, the primary inductor has a power source, which is the generator, right? And the secondary inductor does not have a power source. It's just a closed circuit. Just like this configuration, that you see right here. See here, the wire is not connected to a power source whatsoever. And we can copy Snipping. This notation here is unfortunate. Let me change this notation to lowercase l. Okay, this one is going to be changed to lowercase l prime. I don't want to confuse the length l with the inductance symbol, right? With the symbol for the letter for the inductance. So here goes, see below. See below. See below. Okay. So now, how do you do that? Okay, now you do exactly the same thing that we did for the primary inductor. Here you go. All you have to do is to repeat this equation, but taking into account that there is a induced current only inside this inductor, okay? And here you go. Well, now what we are going to have? We're going to have an induced voltage in the secondary inductor, and that induced voltage is going to be equal to the number of turns of the secondary inductor. Did you notice that I put that N sub S, right? Times the flux, the magnetic flux through the secondary inductor. Okay? But now the magnetic flux through the secondary inductor is going to be what? It's going to be the magnetic field of the primary inductor. Because it is the primary inductor that has the magnetic field, that's producing the magnetic field. So this subscript doesn't change. What's going to change is going to be this area. This area is no longer going to be the area of the primary inductor, but it's going to be the area of the secondary inductor. The flux through the secondary inductor is going to be equal to the magnetic field of the primary inductor times the area of the secondary inductor. And now we can continue the equation. This term doesn't change because it's the magnetic field of the primary inductor, but this term here does change, right? This one also change. Let me put NS for everything. Here you go. So you don't miss anything here. Okay. What else? Okay, this term here goes outside because it does not depend on time. This other term goes outside as well because it doesn't depend on time. And we no longer need the parentheses. Here you go. And now I can copy everything here and paste. Wait a minute, I did something I was not supposed to do. Yeah, okay, I gotta go next step. Yeah, let's keep this way. Otherwise, I'm gonna lose the steps here, right? This term here goes outside the parentheses, and then I gotta use this, right? And this area goes outside the parentheses. I replace the AP by the AS. Okay, and I get this di dt, delta I, delta t, right? And now I can finish my calculation. Here you go. Do you see the difference? Now there is a difference between the equation for the self-induction and the equation for the mutual inductance. Okay, and now here you go. The induced voltage in the secondary inductor is going to be M times delta 2Q delta T2. And by the way, the M is going to be equal to that. I want to compare the self-inductance with the mutual inductance, okay? M equal, look how there is a difference between those two equations. They're very similar, but there is a difference. There is a difference. They're not exactly the same, but they remind, right, what's happening. See the difference from mutual inductance? we have the number of turns of the secondary inductor and the area of the secondary inductor. For the self-inductance, we have the number of turns of the primary inductor and the area of the primary inductor. This term here doesn't change, right? This one is a universal constant, and this one doesn't change because the magnetic field is coming from the primary inductor. Okay? So that's the difference between self-inductance and mutual inductance. And now we can put, okay. Notice that is dependent only of the geometrical parameters of the device. Okay. What else do I have to tell you about that? I have to tell you that the unit of this thing. Yeah, let's talk about the unit. Okay. That the genetic equation is this one here. I'm just going to repeat this. I consider that so important that I'm going to repeat it in this lecture. Because ideally, I should be showing this actual device, right? Okay, so here you go. The equation for the capacitance, right? The voltage in terms of the capacitance, the voltage in terms of the resistance, right? And the voltage, the induced voltage for a single inductor, the induced voltage for two inductors. Okay, the general equation is something like that, right? Electric potential. There is a parameter that depends on the geometry of the device, and my delta Q over delta T is raised to a given power, where N is equal to 0 for the capacitor, N is equal to 1 for the resistor, N is equal to 2 for the inductor, either mutual or self-inductance, or either mutual or self-inductance. Now, what else you have to know? You have to know about the units of mutual inductance and self-inductance. Their units are exactly the same, okay? Doesn't matter if you do for primary or secondary, because if I change it, when I even put it here, P, S, P, S, right? I'm gonna copy and paste here. Copy and paste here, okay? The number of turns has no units whatsoever. So I'll write down the units as being the unitless unit. 1. This term here is the number of turns per meter, per unit of length. So I put 1 over meter. This term here, which is a universal constant, has units of Newton over amperes square. And this one here is just the unit of area, meter square. Newton meter, A square. Newton meter is joules, right? I should go the next step here. Newton meters is joules. Here you go. Joules per area. Okay? Now, this unit shows up so frequently in electricity and magnetism that we give it a name. We call it the Henry. Okay? In honor to the guy that discovered electromagnetic induction together with Faraday, right? Independently of Faraday. Henry was in the United States, Faraday was in England. At that time, England was the superpower of the time, until the end of the Second World War, okay? We have history behind that. So that's what I want to explain to you. I want you to have a very clear idea what self-induction is and mutual inductance as well. It's 10:32. I want to go to let's see, we have the next one that we're gonna, let's see if we can finish before the break, right? Transformer. Yeah, there's gonna be transformer. Yeah. So I'm gonna copy and paste chapter 22, just to remind you. what we've done so far for chapter 22. You go get rid of this guy. Okay, so here you go. We did induced electromagnetic force, induced electromotive force. Electromotive force is just another name for the voltage. Okay, just another name for the voltage. Voltage provided by a source. And induced current, we covered that. Motional EMF, we covered that. As the area increases, right? The magnetic flux through that area increases as well. Okay, and that's what magnetic flux is all about. Faraday's law of electromagnetic induction. If the flux changes in time, then we do have an induced current or an induced electromotive force. The direction of the current is given by Lenz's law. We skipped 22.6. We talked about the electric generator. I even showed to you that simulation and gave you a link for that. And we just talked about mutual inductance and self-inductance. Okay? And now we're going to talk about transformers. Transformers is a very important device. We have transformers all over the place. We need transformers to feed our houses. Okay, and with electricity. And there is a reason for that. Okay, so, before we talk about transformer, let's talk about the magnetic energy, right? I didn't talk about the magnetic energy. I almost skipped. Energy, so here you go. Energy is stored. Energy is stored in a device. Okay? Okay. We have electric energy, electric potential energy, and also now we have this new type of energy that's called the magnetic potential energy. Okay? The electric potential energy can be stored in a charged capacitor. Okay? Capacitor is an electric device. Whereas the magnetic potential energy can be stored in a charged inductor. Charged inductor. Now, do you see why we study inductors? Because those are devices that can store energy. The resistor doesn't store energy, okay? The resistor does not store energy. It only consumes energy. Only consumes energy. Okay? What we saw before, we saw that for a capacitor, we have the following relation for the potential energy stored by a capacitor. It's half CV squared. It's not difficult. And by the way, this is the equation. This is the energy. This is the energy stored by a parallel plate capacitor. Parallel plate capacitor. The above equation, if you remember the above equation, we did that here in the classroom, right? The above equation can be rewritten in terms of the energy density, okay? The energy density is what? Delta U over delta V, where V is the volume of the device. Okay, so here you go, delta U over delta V. Like that. And when we do the math, we get this simple result. Okay, directly proportional to E squared. Although this equation, and then we did that before, right? We derived this equation before. Although this equation was obtained for a parallel plate capacitor, comma, it also applies to any type of capacitor, whether it's the spherical, cylindrical, etc. Okay? We're going to do the same thing for the inductor. Okay? For the inductor, we use a similar reasoning. Here you go. Recall, right? Recall that the delta U over delta Q is the voltage. But in this case, our voltage is going to be the induced voltage. Going to be the induced voltage. And now we try to put this equation into a different format. And the different format, what is the different format? We separate the potential energy, right? Multiply by the charge, and then recall that the induced voltage can be rewritten in terms of the self-inductance. Here I'm doing for just a single inductor, right? Negative sign here, negative sign here. This equation again that you see here is nothing but Faraday's law, written in terms of the inductance. Okay? What is the next step? Okay, in the next step, we can cancel out the negative signs. Okay, like that. And then there's a really nice trick, mathematical trick that we can do. Okay, and what we're going to do? I'm going to take out this delta I from the numerator and put this delta Q on the same place as the delta I is. Okay, that's the mathematical trick that we use to derive better equations. So what we end up getting here, now recognize that what you see here is the current, right? Recognize now that what you see here is going to be the current, right? Which is also be a function of time. Current and delta current. What's the next? And by the way, I'm going to put that in terms, I'm going to do what? I'm going to do something else. In order to recognize that we are doing a derivation for the inductor, I'm going to put the magnetic subscript on the potential energy. Okay? And now, okay, go. What else do we do? We have this relation, right? And what I'm going to do, I'm going to pass this delta I to the other side. There's a reason for that. There's a mathematical reason for that. You get delta I. And then we plot that along the y-axis and this one along the x-axis. Okay? By plotting, you go. By plotting the left side with the right against I, we get a straight line with slope equal to L. Okay? The slope equal to L. That's gonna look like just something like that. delta UB over delta I and I. Okay. And now we recognize, okay, that this area here is going to be nothing but the total magnetic potential energy. Okay? That's what this area is going to be. So we can start thinking in terms of infinitesimally small rectangle right here. Infinitesimal rectangle, infinitesimally small rectangle right here is going to be delta UB only, right? Because my I becomes delta I. And this delta I right here is going to cancel the other delta I there, okay? And then if we consider the whole area is going to be the total potential, magnetic potential energy. Okay, so that's the little trick that we do. A rectangle infinitesimal side delta I below this line has an area delta UB. Let's see if I have here. Oh yeah, here you go, I have it here. That's what I call infinitesimally small rectangle. Okay. So here you go. This area here is going to be exactly a delta UB. Consequently, the whole area is going to be the whole potential energy. The whole magnetic potential energy. In mathematical terms, it's going to be, you know, half of I, right? Li. Total will be given by the total area below the straight line, which is the area of this triangle. Half I UB, delta UB, delta I. Okay. And delta UB, delta I is going to be Li, which is end up being Li squared, half Li squared. And that's what you got. One more students coming in. Okay, so here you go. To find the total magnetic potential energy is going to be half Li squared. To find the energy stored in a capacitor is half CV squared. See here, again, we have, you know, the parameter associated with the device, the parameter associated with the device, okay? The parameter that's responsible for the energy in the electric device, and the parameter that's responsible for the energy as well in the electric device. The V is what generates the electric field. The I is what generates the magnetic field. Okay. Now we repeat exactly what we did for the capacitor. Okay, now let's continue. Let us continue our derivation for the solenoid, right? By the same token that we derived the energy density of the capacitor using the parallel plate capacitor, we are going to do the same for the solenoid with a uniform magnetic field, right? So here we go. We start, our starting point is the potential energy of the solenoid. In our next step, we are going to write down the inductance, right? The equation for the inductance, remember? The equation for the inductance, it was what? I'm going to write it down here before. The primary, right? And number of turns of the primary times the density of turns of the primary inductor. The density of turn of the primary inductor is nothing but N sub P divided by L. Okay, I'm going to go. So when I combine NP with NP, I get NP squared. Okay, so here we go. NP squared, I can erase that. I have the I, should have the I squared here. My A that you see here is A sub P. I'm not gonna put it here, so I don't need to complicate the equation, right? And what else do we have to do? We have to do a little mathematical trick here. Remember, I'm going to write it down here below. Remember that we want to derive the energy density, which is the energy per volume of the device. So we have somehow to get a volume there in this equation. There is a way of getting there. So we must somehow get the volume parameter in the above equation. Okay, we already have the area. We already have the cross-sectional area of the device. All we need now is the length of the device that when multiplied by the area becomes the volume. So what do we do? All we have to do is to multiply the equation and divide by L. Here you go. That was the equation. Here you go. Multiply by L and divide by L. So we do not change our equation. When we do that, the L downstairs becomes L squared. And the AL upstairs becomes the volume that I'm going to represent by the lowercase v. Okay? V for volume. And there's one more simplification we can do here. Notice that now NP squared divided by N squared can be reduced to lowercase n squared. Number of terms per length, right? And now that we have the volume here, we can pass to the other side to get the energy density. Okay. UB, I'm gonna put it here. Here we go. Pass the volume to the other side. We get the energy density of the magnetic field. Energy density. No V on the other side, which is proportional to the square of the current. If you double the current, the energy increases by the square. Have you thought about that? Okay. But then we can rewrite this equation a different way as well. Okay, there's another way of writing down this equation. Very, it's a very intuitive way by, just by using the equation for the magnetic field. I'm going to rewrite this I, this current, in terms of the magnetic field. Recall that I told you the magnetic field is always proportional to the current, right? So when I write down the I in terms of the magnetic field and substitute here in this equation, like I said, we are going to get a very intuitive result that's very similar to that of the capacitor. Okay, and what I'm going to do here, I'm going to put my I here and square, right? I'm putting my I inside the parentheses so you can see my derivation. And this I, B over mu naught N is placed there in the parentheses. Okay. Look what's going to happen to the N. The N is going to disappear because it's raised to the second power, right? Let's do the next step. Here you go. B squared, mu naught squared, N squared, lowercase n squared. We do not need the parentheses anymore. We do not need the square in the parentheses anymore. And the lowercase n cancels out with the other lowercase n. And look what we get. The mu naught here upstairs cancels out with the mu naught square downstairs. And we kind of get a similar relation, a relation that's rather similar to reminiscent of the energy density of the electric field. Okay, here you go. Energy density of the magnetic field, right? Energy density of the electric field. The only difference is that the constant is downstairs, right? Epsilon. Epsilon. Here you go. And instead of B, we have E here. Instead of B, we have E here. See how they are very similar to each other? If you memorize one, you can memorize the other. Okay? Okay, so let's see. Are we going to do transformers? Well, we were running out of time here. Looks like we have to finish transformer next time. Okay? And let me take attendance now. Today is the 16th. Abir Ahmad, are you there? Hello, Abir.
Hi, I'm here.
Thank you.
Thank you.
Nestor Alvarado, are you there, Nestor?
Yeah, I'm here.
Okay, thank you. Monte Ambarshan.
I'm here.
Thank you. Isabella Ballestero. Isabella BE. I don't see Isabella here. Okay. Next is Justus Bolden. Let's see. Are you there, Justus? I can see Justus here, but he's not, looks like he's away from his computer. Alexandra Barmistrova. Are you there, Alexandra? Justus. Okay, thank you, Justus. Doesn't look like Alexandra is here. Benjamin Carvajal. Thank you, Benjamin. Elizabeth Castellano.
Here.
Thank you. Natalia Cordoba. Thank you. Jacqueline Delgadillo. Thank you, Jacqueline. Jenny Diaz.
Here.
Thank you, Jenny. Valerie.
Here.
Thank you. Next is Juan Escalera. Hello, Juan. Okay, thank you. Bianca Eloki.
I'm here.
Thank you, Bianca. I saw BE there, Bianca, and then I was wondering who is BE, you know? And now makes sense, right? BE for Bianca Eloki. Okay.
Yeah, my cat signed me off from the computer, so I had to log in through my phone.
Okay. Here you go. Next is Edwin Gonzalez.
I'm here.
Thank you, Edwin. Ellie Gonzalez.
Here.
Thank you. Next is Manuel Hernandez. Thank you, Manuel. Samantha Hubert. Are you there, Samantha? No, doesn't look like. Okay. Next is CJ. CJ, I don't see CJ here. Amber Lopez. I don't see Amber. Arely Lopez.
I'm here.
Thank you. Genesis Lopez. Hello,
I'm here.
Thank you. Mary Kaelia. Hello, Mary. Okay, I'm gonna put the star here on Mary's name. Galia, are you there? Looks like your mic is not working, Galia. Please type there in the chat window. If I don't hear from you, I'm gonna put a star in your name. Ramon Olivares.
Here.
Okay, Taylor Thorne.
I'm here.
Okay, and Manuel is here, right? Manuel Hernandez. Okay, I already gave you attendance. Manuel. Next is Jeremy Pittman. I don't see Jeremy here. Stephanie Ramos. Thank you, Stephanie. Leslie Rios.
Here.
Thank you. Jason Strait.
Here.
Thank you, Jason. And Hema Torres Navarro.
Here.
Thank you, Hema. And okay, so let's have our break now. 23, 24, 25. Mary Michaelian, are you there? Mary and Galia. Okay, let's have our break now. It's 11 o'clock. Break. 11 a.m. to 11:15 a.m. Okay? So I see you in 15 minutes. Share. Screen one. Good. And we should get the notes for lab number 4. Make sure you all got the spreadsheet. If you didn't get, let me know. Okay. Let's see. Trying to get my notes here for lab 4. Just hang there with me, please. Ah, looks like I got it. Okay, so here we go. Let me see, Monte Ambarcian. I have to stop sharing my screen again. So go. Monte. Yeah, I uploaded Monte. It's supposed to be there. Try it again. You know, refresh your screen, right? And now I can go back sharing the screen. Insert page break. Okay, let's start with lab number 4. Okay, so let's just review what we have done so far, right? Labs 1 and 2, right? We mapped the electric field. We mapped, so not the electric field, the equipotential surfaces. In this case, it's not a surface, but it's equipotential lines of 2 different electrode configurations. Okay, one was the parallel plate, and the other is the concentric cylinders. 2 concentric cylinders. The 2 concentric cylinders. Lab 3, we let's see, we measured the resistance of different resistors and compared these measurements with the color code, and then we also call nominal value. Color code or nominal values. With during these experiments. Did you find it, Monte? Did you find the spreadsheet? Did you manage to get the spreadsheet there?
I found it, yeah.
Okay, good. Thank you. During these experiments, I introduced you to different equipment and devices, right? Equipment and devices. Different equipment and devices. Okay, here we will continue with this introduction. And how are we going to do? By putting together the simplest circuit you will ever find in your life. A circuit with a single resistor. Okay. So what is the list of materials? One is the resistor. You're already familiar with the resistor, right? I showed you how resistors look like. They're sold out there. They're mass-produced devices because they're mass-produced. The advantage of mass-produced devices is that they're very inexpensive. They're very cheap. Resistor can be bought for 10 cents, maybe even less, depending how many resistors you buy. I introduced you also to digital multimeter. Digital multimeter. We use the digital multimeter in labs 1, 2, 3, and we're going to use it in lab number 4. Resistor we have used only in labs, in the lab number 3, right? And we're going to use it lab number 4. We didn't use a resistor in labs number 1 and 2. So what else we are going to need for this lab? We're going to need a power supply. We use the power supply in labs 1, 2, 3, and 4. Okay? We needed a power source, a power supply, the battery, right? Power supply / battery. Okay, and we're going to use cables. And we're going to use 2 black cables and 2 red cables with banana plugs. Banana plugs. And we also use those cables, black and red, in labs 1, 2, 3, and 4. Okay, so that's the equipment. And let's take a look at the illustration for the labs. Lab correction, illustrations. Let's see, no, not here. We want lab slides. Want to do single resistor. Okay, here you go, power supply. We start with our power supply. And the idea here is to build a circuit with a single resistor. And here you go, and the objective, right? Objective of this lab, to verify Ohm's law. Ohm's law is V equal to Ri, using a circuit with a single resistor. Okay, that's the objective of this lab. In order to verify that, we must measure the voltage applied to the circuit, the resistor used in the circuit, the voltage applied to the circuit, the resistor used in the circuit, and the current in the circuit. That's what we have to do. We're going to measure all those 3 parameters using the multimeter. Okay? And very important, now that we are going to measure current, we haven't done that yet. Okay? I have to warn you about the way that we measure current in a circuit. Okay? So far, we have measured only voltage and resistance. Okay? In both cases, we connected our DMM in parallel to the device in question. Okay? That's what we did. Now we will have to measure current. In order to measure a current, remember that, in order to measure current, the DMM must be connected in series with the circuit. Okay? Recall that, remember that, okay? Voltage, to measure voltage, to measure voltage, comma, the voltmeter must be connected in parallel to the element, okay? To the element of the circuit. To measure current is all the way around. To measure current, the ammeter must be connected, not in parallel, but in series. In series with the element of the circuit. And I'm gonna show you how to do that. Okay. And I'm gonna get, but first let's open one of the spreadsheets that we're going to use. And I wanna make sure everybody got his her spreadsheet. Okay, let me know. If you didn't get, let me know. Lab right in here.
I can't seem to download my Professor.
Who is that? Nestor?
Nestor? Yeah.
Okay, so let's see. Am I sharing the screen? Not yet, right? Let me check. Every time I go back to the canvas, I have to stop sharing the screen. Okay. So anybody else didn't get the spreadsheet? I want to hear from you. Only Nestor, right? So let's go here. Every time that I gotta go to here to canvas, I have to turn off the sharing of the screen because I have to go to a place where you're going to see everybody's grades, you know, and I'm not allowed to display. Let's see, Nestor, see, it shows here that I uploaded the lab report for you, Nestor. You know, try it again. Try to download it again, okay? It's lab speed lab report. Try to, you know, go there again. Go to lab.
I got it, Professor. Sorry about
Okay.
that. I guess it was my Wi-Fi, but I got it.
Okay, thank you. Okay, now let's go there to the start sharing the screen again. Here you go. Lab number 4. Here you go. Let's take a look at lab 4, group number 8, right? Whoever has group number 8 there, you're going to be familiar with this. The numbers here are going to be the same, okay? So here you go. We have this table here with the resistance value of your resistor. We have this other table here with the voltages being displayed by your power supply, the voltage measured by the multimeter, which by the way is supposed to be very close to the voltage provided by the power supply. However, those two values will have to have different significant figures because those are different devices. We have the current connected in one way, the current connected in the current measured, right, by the DMM when it is connected directly to the positive polarity of the power supply, and the current measured by the device, by the DMM, when it is connected directly to the negative polarity of the power supply. And here's the average, okay? Average current. All of that, everything that you see here are measurements, okay? So let me see here. Everything in yellow is going to be actual measurement. Everything else are going to be calculations, and I'm gonna put in a different color, okay? Data highlighted, here you go. in yellow are actual measurements, okay? Data highlighted in orange are, how do I call it? Results, are results. By results, I mean measurements that were processed, okay? By process, I mean multiply, divide, summed up, okay? So here you go. This average current that you see here is just the average of those two independent measurements. What you see here is the power consumed by the circuit, or even provided also by the battery, is the voltage times the current. Again, here is a result. It's not a measurement, okay? And here is the resistance, but it's the calculated resistance. It's not the measured resistance. I'm using the measurement of the voltage and the measurement of the current, right? To find the resistance value. So here you go. Measurement, results. And what else do we have here? You know, the third table that you're already familiar with. The table related to the plots that we come up with. Number of data points, regression equation, R squared, and then CL, min and maximum. And then the slope. Okay, you gotta write down the slope values of your graph. The value should be right in here, and the units should be right in here. And then we're going to compare with the percentage difference of the resistance measurement independently. That's what we're doing here, okay? So here we go. To measure voltage, voltmeter must be connected in parallel to the element of the circuit, right? To measure current, the ammeter must be connected in series to the element of the circuit. And I'm going to see how we make this measurement. But let's start with the procedure now. Procedure. Measure the resistance of the resistor with the multimeter, right? We can measure resistances with the multimeter. Let me see if it doesn't look like I illustrated it. Yeah, unfortunately, I didn't illustrate it. Yeah. So let me illustrate it here for you. Measure the resistance. The resistance with the DMM. Okay. So here you go. And I'm going to get this. Here you go. Here's one of the multimeters that we have there in the college. It looks exactly like that, okay? The small box with all those color codes that you see right in here. How do we measure resistance? We get a multimeter, set it to measure resistance, and connect the cables. Here you go. The probes of the multimeter. Connect the probes of the multimeter to the resistor, something that we did in lab number 3. Here you go. Now I measure resistance. Oh, like that. Okay. Set the multimeter to measure resistance, right? First you gotta set the multimeter to measure resistance, and then connect the leads of the multimeter to the ends of the resistor. And then, you know, when you do that, you log in the value of the resistance right in here. In this case, the value was 723.7. The unit of resistance is the ohm. So that's the first step. Okay. The next step, you know, plug. Now we're going to put together our circuitry. Okay. Plug the red banana cable into the red output of the power supply. That's the next step. I'm going to illustrate that here in my, okay, measure resistance, power supply, red banana cable, connect to the resistor. We usually use an alligator clip to connect the banana cable to the resistor, and then close the circuit with the black cable, also using an alligator, right? An alligator. Here you go. This thing here, this pointed thing here means the alligator clip. Okay. So in a regular circuit, a schematic of the circuit looks just like that. Power supply, which is set at 10 volts, connected to a resistor, and the circuit is closed. So 11:50 right now. Let's take a break. Right, let's take a break. We have been almost 1 hour here, and then we continue break from 11:50 a.m. to 12:05 p.m. Any questions so far? Okay, I'm assuming that everybody got their spreadsheet, and we will be back in 15 minutes. See you soon. Okay, I'm back here. And let's continue here with the step-by-step, how we perform this experiment. Okay, plug the red banana cable into the red output of the power supply, right? And connect the other end of the red cable to the resistor. And I can add, in addition to the two black cables, let's also write that down here that we two alligator clips, right? We need the alligator clips to connect to the leads of the resistor. Connect the other end of the red cable to the resistor using an alligator clip, Black cable with banana termination. Black cable with banana termination connect to the black plug of the power supply, right? And connect the other end of the black cable, to the other end, to the other end of the resistor using an alligator clip. And that's exactly what this drawing here shows, okay? Right now, at this very moment, we do have a circuit flowing into this, we do have a current flowing into this circuit. And the current is flowing clockwise in this drawing, like that. No? The power supply is set at 10 volts, but, well, the current is flowing, but we should not know what the value is because we didn't connect our multimeter yet. We didn't connect our measuring device yet, okay? Now we are going to connect the measuring device to the circuit, and we will have to modify the circuit, okay? Connect the DMM, connect the DMM in parallel to the resistor. Okay, first we're going to connect the DMM in parallel to measure voltage. Whenever we're ready to measure the current, then we will have to connect it in series. Okay, connect the DMM in parallel to the resistor to measure the voltage. Measure the voltage. Here you go, and it looks just like this drawing here. Here you go. DMM, red cable, black cable. Okay, red probe, black probe. The probes are just like cables. regular cables. And then you're going to display the voltage that you see here, which is going to be close to 10 volts, okay? It's going to be close to 10 volts. And that's, well, and that's what the next step here. Let me copy and paste here. You go, take your voltage measurement with the multimeter. You start with 10 volts. Start with 10 volts in the power supply. Okay? Then change the potential to 864 2.8 volts and take the voltage measurement with multimeter. Start 10 volts in the power supply and measure the voltage in the battery, in the resistor with the DMM. Okay, and that's where we have right here. Here we go. We start with 10 volts. Don't forget, it's 10. This column here is the voltage that you see at the power supply. The power supply has a LCD screen that tells you what's the voltage that's providing there. So, but I need you to, don't forget, I need you to display it with the proper number of significant figures using that table that I provided you. Let's take a look at the table again. Let's see, sig figs. That here, no, is that here? Let's see. Lab correction, not here. Well, I cannot find them right now, but it's there in the in Canvas, okay? Let's see, is it here? It's supposed to be, just supposed to be here, but I cannot find right now. But anyway, in the table, I'm going to write that down here for you. In the table, in the table that I provided you, let's see. This one here, P07 sig figs, okay? P07 sig figs. So number of significant figures, resistance for the DMM, right? Here's the number of significant figures for the voltage as is seen from the little screen of the power supply, okay? If the voltage is between 0.1 volts and 0.99 volts, you have two significant figures. If the voltage between 1 and 9.99, you have 3. Okay, so remember, this is for the power supply, and this is here the measurement of the voltage using the multimeter. Okay, the two devices, they display the voltage with different number of significant figures, and that's what you have to display right in here in this column. This column is the voltage for the power supply, and this column here is the voltage as measured by the DMM. Okay. 10 volts. So you make measurements that with the power supply set at 10 volts, 8 volts, 6 volts, 4 volts, and 2.8 volts. That's what we do. So you have to adjust the knobs there in the power supply and take the measurement with the multimeter, right? Okay? And then what do you do? After we are done with that, all we have to do, here you go. That's the schematic, the electric schematic. The voltmeter in parallel is the resistor. The voltmeter is nothing but your digital multimeter. Okay, all we have to do now is to invert the polarity, to invert the flow of the current, okay? And when we invert the polarity, the multimeter here is going to display a negative voltage. And then you repeat, right? We went down to 2.8, now we go up to 10. The negative sign means that you inverted the polarity. The negative sign is exactly what the multimeter provides you when you invert the polarity. Okay, so we measure the voltage. And now we're going to measure the current. And to measure the current is a little bit more difficult. We have to break down our circuit, okay? We have to break down our circuit and start from scratch. Here you go. Red cable, multimeter. The multimeter is going to be in series with the circuit. Now note, see that we are connecting the red cable to this yellow plug in the multimeter. Okay, the multimeter has two different circuits, has two different internal circuits. The internal circuit that you access through the red and black leads, which is to measure voltage and resistance. And then we have this other one here, that is the yellow and black plugs. This one is to measure the current. To measure the current, you have to use a different circuit in the multimeter, okay? So here you go. Black cable in the black plug connected to the resistor, and then you close the circuit. Now your multimeter is going to measure the current. Because the multimeter is connected to the plus side of the power supply. You know, I call those measurements the I plus current. I plus for current connected to the positive side of the ampere of the multimeter. And we have all those measurements as I vary the voltage from 10 to 2.8, and then inverted the polarity, right? I have negative current. All those current values can be displayed with the proper numbers of significant figures, and you have to find out what would be the number of significant figures according to this table here. Okay? So, repeat, here you go. That's how the schematic looks like, the electrical schematic of the circuit. This circle is the A, is the amperimeter, right? I mean, or the ammeter or amperimeter, which is nothing more or less our digital multimeter. That's why it's called multimeter. It acts as a voltmeter, it acts as a ammeter, it acts as a device that measures the resistance, ohm meter, and so on. Okay, so here you go. Let's skip that. Yeah, you never connect the circuit in this way, otherwise you can burn your multimeter, okay? Look here. Note that the yellow is connected right here. Never connect your circuit this way, otherwise you're going to burn. Otherwise, you go. Otherwise, you can damage. Otherwise, you can damage your DMM. And by the way, this is a mistake that we see all the time in the lab. Students connect the ammeter in parallel with the circuit. It's much easier to connect the device in parallel than to connect it in series. And even professors do sometimes make this mistake, right? A couple of students are reporting issues their Zoom and can't log in. It shows Zoom is down on their end. They all wanted you to know that so you did not think they were absent. Let me see. Okay. And anybody else who's having who is having problems with the Zoom? I want to know who is having problems with the Zoom. I'm gonna ask you one by one, okay? I never had this problem before, so I'll be interested to find out who's having this problem. Was earlier, kept crashing, but it seems fine now. Anybody else? It looks like, did you have any problems, Monte? Did you also have this problem? Okay. Monte, what you booted out before, Monte? Okay, so Monte didn't have any problems, so let's see here. Zoom, right? That's 460, lab 4. We're messaging, speaking about it, such as Nestor. It's fine. Okay, Elizabeth, what you booted out anytime, Elizabeth? I'm gonna go through everyone, okay? When I start to go through the classroom, and then I'll ask you this question, and let's see how spread out, how bad the problem is, okay? So he go and going back here, I'm gonna write that down. Never connect, I'm gonna put it here. Never connect your ammeter, the DMM set to measure current in parallel with your circuit, okay? Never connected. Ammeter connects in series, ammeter connects in series, voltmeter connects in parallel, okay? And this should go in the next, okay, to measure the current, we must change the circuit configuration. Starting from scratch, we do the following. Here go, red cable to red plug, here go, right in here. Red cable to red plug, just like the picture that you saw. Never connect your ammeter, the DMM set to measure current, in parallel with your circuit. And the same applies to the voltmeter. Never connect your voltmeter set to measure voltage in series with your circuit. The voltmeter is not gonna burn out, but if you measure the voltmeter, will not burn out, but you will get a zero measurement. The problem is whenever you're using the DMM as a ammeter. Okay, so he goes. Now we're inverting the polarity to get the negative current, okay? And then we set up the ammeter on the negative polarity of the power supply. And when we do that, you're going to see that you get almost the same measurement, okay? You get almost the same, you just change the position. Initially the position was here, and then the position was here. You get it, almost the same measurement, and that's what the A plus and A minus is all about. We take the I average, okay, and so on. And then what you have to do now? Now you have to plot your graph. Okay. Plot V1 along the y-axis, okay? Plot V1 along the y-axis and I average along the x-axis. So that now you have something to do. Okay. So why are we doing that? Okay. The relation is what? Ohm's law is V equal to Ri. When we plot V along the y-axis and I along the x-axis, right? You should get a linear equation, which is like plotting the y against x in this equation. You should get a linear equation with a slope equal to R, the resistance. And then this slope that you get with the graph, you're going to compare with the measurement that you got before right here in this picture, okay? So go ahead, I'm gonna give you some time to do the plotting. Here you go, V1 and I, okay? Don't forget, I want the I average in the x-axis, okay? So here you go. I want the V1. Do you see that you get exactly a straight line? Remember, this is real life measurements. I didn't make up this data. But let's not forget that I want I along the x-axis, right? I is not along the x-axis. It's the v that's along the x-axis. So you have to, you have to do something here to plot the graph in the proper way. That is one of possible ways to do that is to switch. Sometimes he doesn't let me do that. It's unfortunate. Sometimes he let me switch manually like that. Okay, but right now he doesn't let me for some reason. Sometimes he let me do that. Sometimes he doesn't let me do that. But there's another way, more reliable way to invert the positions of this. To get notice that the v is in the x-axis, right? I don't want the v in the x-axis. I want the v in the y-axis. So what do we do? Step by step, right? Click one of the dot lines, right click it, select data, and now you should be familiar with this window, right? This window tells you how the data is plotted. Notice that x values here in the column G is in the x value. Column G is the voltage. You don't want the column G in the voltage. You want the column J in the x value. Okay, and then you swap right here. Instead of J, you put G. You get the idea? Let's cancel it. Gonna do that again. Here you go. Edit. G and J, right? G is the V, J is the I. Okay? So you want J as the X value, and you want the G in the Y value. Okay, and now I got it right. And then you should get, the regression equation and the trend line. Linear, display. And if you did everything right, now this slope that you see right in here is going to be very close to the resistance that you get in your measurement. Okay, you see here 734.5, right? 734.5 is very close to 723.7. And you want also to increase the number of decimal places of your R square. Format trend line label. General, you put number, put like 5 decimal places. Let's see if we get yeah, good. We got an R square that's different than 1. Okay? So now I'm gonna call you one by one. Zoom Lab 4, okay. Abir Ahmad, did you download your spreadsheet, Abir? I'm gonna put here download. Download. Is Abir there? Okay, Abir is not answering. I'm gonna put it here, star under Abir's name. Nestor.
No, I'm here. I'm here.
Okay,
yeah.
Good. Did you have any problems with the Zoom? Were you kicked out from the?
No, I didn't.
Okay, you weren't. Good. What about, did you download their spreadsheet?
I'm sorry?
Did you download your spreadsheet?
Yeah, I did.
Good. Did you plot your first graph?
Yes.
You did also?
I'm sorry? Oh, no, I haven't plotted it. Not yet.
Okay, good. So don't forget, plot the graph, right? And then invert the X and Y axis, right? Now let's go, Nestor. Did you have any problems with the Zoom?
I'm sorry?
No, now I'm calling Nestor. Nestor.
Yes. Wait.
Okay.
Okay. So I could hardly hear you, Nestor. Doesn't look like he's here. Yeah, okay, so doesn't look like he's here. Nestor Alvarado, let me see here, Alvarado. Yeah, make sure that you have a reliable internet connection, okay? And I never had any problem to this connection, Zoom connections, unless there is outage, electricity outage. But even with an electricity outage, I have a UPS device here. So, make sure that you have a reliable internet connection there at home and a reliable computer as well. Okay, so let's see, Monte. I talked to Monte, right? You didn't have any problem, right?
I didn't have any problems, no.
Yeah, okay, you didn't have any problems. Zoom, no problem. Okay, and did you download the spreadsheet?
Yes.
Okay, good. Did you plot your graph already?
Not yet.
Okay, so you're working on that. That's good.
Yeah.
Thank you. Isabella, is Isabella there? I don't see Isabella here. Next is Justus. Hi, Justus. Are you there? Yes, I downloaded the spreadsheet. I had no issues either. Okay, so see that? Downloaded, yes. Did you plot your graph already? Have not. Okay, you're working on that. Thank you. Alexandra? Alexandra is not here, right? Thank you. Good. Benjamin Carvajal. What happened to Benjamin? I don't see Benjamin here. Looks like Benjamin's no longer with us. Okay, out. He was initially here. Elizabeth Castellano.
Download the spreadsheet.
Okay, did you have any problems with the Zoom?
No.
Okay, no problems with the Zoom. You're working on the plot?
Yes.
Good, thank you. Natalia Cordoba. Had no problems with Zoom. Okay, see that? Things works reliably here. Did you download, Natalia? Did you download their spreadsheet? Working on the first graph. Okay, since you're working on the first graph, then you're able to download. Okay, thank you, Natalia. Next, Jacqueline Delgadillo.
I haven't had any problems.
No problem. Okay, did you download their spreadsheet?
Yes.
Okay, did you plot your graph already?
Not yet.
Okay, thank you. Jenny Diaz.
I don't have problems soon.
No problem with Zoom. Good. Did you download their spreadsheet?
Yes.
Good. Are you working on your plots?
I finished it.
Oh, you finished. That's good. So let's see. Now tell me, did you invert the axis too, Jenny?
Yeah, I did.
Okay. And now tell me, what's the slope that you're getting there from the equation?
I'm the slope. I'm getting 1,222x plus 0.059.
Okay,
And then my R
just the slope, okay? Just the slope.
Okay.
Is that 1,122?
1,222.
222?
Yeah.
Like that?
Yeah.
Okay. And okay, 1,222, and then you go ahead. I want you to plug this value right in here at this last table, okay? This slope,
Okay.
1,222, and look for the percentage difference. What you get for the percentage difference, okay? Type it there. Let me know what the percentage difference. I'm gonna do that with everybody else. Percentage difference. What are you getting for the percentage difference? Can you tell me?
I'm getting 2.
2%. Okay, good.
Yeah.
That's a good result. Great. So let's go to the next one. Valerie. Hello, Valerie.
Hello. Hi.
Okay. Okay. Do you have any problems with the Zoom? Do you have any problems with the Zoom?
No.
No, right. Okay. What about, did you download your spreadsheet?
Yes.
Okay. Did you plot your graph?
Yes.
Okay, did you invert the axis of the graph?
Yes.
Yeah, okay, good. What's the slope that you're getting?
1998.
1998. Okay, now I want you to get this number and put there in the last table, right? The value and check and tell me what's the percentage difference that you're getting. You type 1998 here, right? And then, read for me what's the percentage difference that you're getting.
Okay. I got 0.78.
Yeah, 0.7, right? Good. So it's a very small difference. That's a very small percentage difference. It's great. Okay. So let's see what I want you to do. Now I want you to, there is just one graph to do it here, right? You can start working on the units if you finish that. Okay. Let's go for the next. Valerie, now Juan Scalera, are you there? 12:35. We have 15 more minutes to go. Zoom is fine for me. I have the spreadsheet. I'm still working on the graph. That's good. No problem. Right? No problem. No problem is Zoom. Zoom problem, right? Let's put it this way. No, you downloaded the spreadsheet. You're working the plot. Bianca Euloki, are you there, Bianca? I don't see Bianca here. So let's see. Mr. Benjamin and Genesis, and the three of them are having difficulty. Okay. Let's see. Next one here, Bianca. I'm gonna put Edwin Gonzalez. Edwin, are you there, Edwin?
Yeah, I'm here.
Okay, good. So are you having any problems with Zoom?
No.
Okay, good.
It was kicking me out, but I was able to get back in.
Okay. Okay, so now did you download your spreadsheet?
I did.
Okay, yes. Did you plot your graph?
I haven't done that yet.
Okay, so it should work. Okay, good. Eli Gonzalez.
Yes, no problems with Zoom. I plotted the graph. I've got the slope and percentage. Slope 1964.2, percentage 0.47.
How much is the percentage difference? 0.7?
0.47.
0.47. Okay, good. Yeah, it's a very small percentage difference. Those experiments that we do with electricity, they provide very small percentage differences. The physics 6 experiments is not as good as the electricity experiments. Okay, I usually sometimes I do get like a 30% difference when I do experiments in physics 6, the mechanics course. But my experience with circuits, it always provides us a very small percentage difference, which is very good. Okay. Now let's go for Manuel. Manuel Hernandez.
I didn't have any problem with the Zoom.
Good.
And I'm working on the graph right now.
Good, thank you. Now Samantha, is Samantha there? No, I don't see Samantha here. Next, CJ. Is CJ there? I don't see CJ either. Amber, did you
Hi.
do you have any problems with Zoom?
It was kicking me out earlier, but I was able to sign back in.
Okay, earlier only. Did you download your spreadsheet?
Yes.
Okay. Did you plot your graph?
Yes.
Okay. You invert the axis of your graph.
I'm trying to do that right now. My Excel is kind of lagging, but I'm trying to do it right now.
Okay, you're working on that. Good. Next is Adeli Lopez. Is that, are you there, Adeli?
Yes, I am here. I
Uh-huh.
had no problem with the Zoom. I
Okay.
already downloaded the spreadsheet and I'm working on the graph.
Okay, working on the graph. Great. Next is Genesis. Genesis, I was told she having problems, right? Problems with Zoom.
Yeah, she's having problems with Zoom.
Okay. Let's see. Emma. Okay. Let's go Mary Michaelian. Are you there, Mary? I'm not hearing from you, Mary. I'm going to put a star here next to your name. Galia? Galia or Galia? How do I call you? Looks like she's no longer here. Okay, Ramon is asking me how to. Oh yeah, here you go. Was early, yes, and working. Good. Are you having any problems with the Zoom, Galia? Not. Okay. Okay, so you download the graph, right? And you're working on your plot. Is that right? You're working on the plot. So let's go. Let me do that again. How to invert the graph, okay? Someone is having a problem there. So if you didn't pick up, here you go. You highlight I average. You highlight V1, right? At this point in time, you should already know how to highlight those two columns separately. Insert. Because the V1 is to the left of the I, what's going to happen? Everything that's to the left is going to end up in the x-axis. But I do not want the V1 in the x-axis. I want the V1 in the y-axis. Here you go. Plot the graph. Right now, we can clearly see that the V1 is in the x-axis because we have a number 10 here. See that? The current is never greater than 1. 0.02. So now how do we invert? Click one of the data points, right click, select data, and then you edit. When the edit screen shows up, take a look at the G, the series X values. The G column is in this X value, so you don't want it in the X values. You want it in the Y value, okay? You can edit it, put your cursor in there and change G to J, okay? And J to, and the other one, the Y value, you can change from J to G, okay? That's how you do it. Another technique too that sometimes works but sometimes doesn't, okay? Another technique that may work sometimes is just click and drag and try to put it to the left side. Sometimes it works, sometimes it doesn't work. At this very moment, this is not working for some reason. Okay. Another thing that you may consider doing, okay, if you have any problems, another thing that you may consider doing is just copy this data, okay? Copy I, okay? Paste it in another column, but make sure you use this one here, this value, 1, 2, 3 value. So you paste the actual numeric value. That's another interesting trick of Excel. Copy the V1 and paste it to the right of the I average, okay? And now just highlight and plot. That's another way. So 3 different ways. Okay, if the first 2 doesn't work, you do this. You do it in this way. And now I have the V in the y-axis. Okay, 3 different ways, right? Let's see if it allow me to invert. Yeah, see, it doesn't allow me to invert. Sometimes he lets me invert. Sometimes it doesn't. Here you go. If I highlight it here, select data. Here you go. Edit. Right. Here you go. Yeah. Okay. And also sometimes this other technique doesn't work. I never knew why. Never know why. P, right? Q. But the surefire way of plotting, inverting the axis is just by copying that and paste elsewhere in the spreadsheet. Okay, and put it in the proper order. Now, who is next? Ramon Olivares. Hello, Ramon. Did you have any problems with the Zoom? I inverted it that. Yeah.
No.
Okay,
No,
so
I didn't have any problems.
no problem, right? Okay, good.
But
So
the
you
invert,
download the spreadsheet, right? And you plotted your graph.
yeah, it's the invert that's confusing me because when I first graphed it,
Uh-huh.
I selected the V1 and
Uh-huh.
then the I, and it looks like your graph, but
Uh-huh.
then you're asking me to invert it, and it looks the other way.
So my question is, were you able to invert the axis? Yes or no?
No.
No. Okay. So do that technique that I mentioned to you before, right? Copy the data. Here you go. Copy the data, and paste it here, to the right of your table. But make sure that when you paste, you right click the mouse and use this icon here, 1, 2, 3. So you paste only the numbers and not the formula. Okay? Because
Yeah,
there's
but
a
my question
formula.
is, when we invert, what are we looking for?
Oh, you want to see the I is to the right of the V, right here in this table. The I is to the right of the V. You want to do the all the way around. You want the I to the left of the V. You want the I, when you put the I to the left of the V, then you plot this set of data, the data set.
Okay. Thank you.
When you do that, then the graph is going to be in the right way. We have 4 more minutes to go. Let's see if I can go through everybody. Right? So Taylor, are you there?
Yeah.
No, do you have any problems with Zoom?
No.
Okay, good. Did you download your spreadsheet?
Yeah.
Okay, did you plot your graph?
Yeah.
Were you able to invert the axis?
I think so.
Okay, what's the slope you're getting?
I got 27,113.
27,113. Wow, looks like a very large number. What's the
Yeah.
percentage difference that you're getting?
1.72.
1.72. Okay, so it looks like you got a good data there. Now start working on the units, right? You gotta work on the units. Sig figs and CL. Sig fig CL. Don't forget to, and let's see, slope. Log is slope less stable, right? Less stable. Sloping less stable. And let's see, Jeremy, are you there, Jeremy? Jeremy doesn't look like he's there. Okay. Oh. Stephanie Ramos. Stephanie Ramos, are you there? Zoom works for me, and I have the spreadsheet just working on the graph. Okay, good. Thank you. No problem with Zoom. Download the spreadsheet, working on the graph. Leslie, are you there?
Yeah, I'm here. I was able to download it, and I don't have any problems with the Zoom, but I'm still working on the graph.
Okay, you had no problem with the Zoom, and you're working on the graph. Let's see, 2 more minutes to go. Jason Straight, are you there?
Yeah, I'm here. I had no problems. I did download it. I got the plot.
Okay,
I was able to invert it.
Were you able to invert? Okay, good. What's the slope that you got?
I got 1,964.2.
64. Okay, good. And what's this? What is the percentage difference?
I got 0.47.
Yeah, see how it's a very small percentage difference. That's showing that your data agrees with your measurement. Okay, your experimental data agrees with your independent measurement that you did of the resistance. That's what it means. And last but not least, Hema Torres, are you there?
Yeah, I'm here. Everything was fine, and I'm working on plotting the graph.
No problems with the Zoom?
No.
Okay, good. So you download the graph and you are working on the plot, is that right?
Yes.
Okay. So okay, so one more minute to go, we have lots of students, okay, in this classroom, so that's why we've spent so much time getting to this point here. And what I want you to do, just work on the unit, significant figures, and CL on your own there at home, okay? If you have any problems with the percentage difference, remember, if you start to get a very large percentage difference, that's because you didn't inverted the axis, right? You didn't invert the axis. So, try to get a feeling of what might be going wrong, right, with your data. Sometimes what goes wrong with the data is just something that you didn't do properly, okay? But this is a very good exercise for you to exercise this ability of troubleshooting. Not just troubleshooting an experiment, but troubleshooting your data too. It's a very important skill to learn. Okay, and if you have any problems, just come by during my office hours or stay longer today and I can help you. Okay, 12:50 right now, and let's see, this lab is due in 2 weeks from now, right? Because we have this is lab 4. Lab 4 is due 2 weeks from now. Because we have an exam next week. Okay. So, and lab 3 is due today. Okay. Do we need more time for lab 3? Report for lab 3. I want to know if you need more time. If you need more time, let me know.
Is there any way you could like make it like do like in a few days? Because I still need more time to do it.
Same here, Professor, if that's
You're
possible.
talking about lab 3? You're talking about lab 3?
Yeah.
Okay. Yeah, I can give you more time. I can give an extension for lab 3. Yes. I'll give you, let's say, another week. Okay?
Yeah, that's perfect.
Yeah.
Thanks,
So,
Professor.
okay, welcome.
Thank you.
Welcome. So I see you next week.
Thank you, Professor. Have a nice day.
You too.
Professor, I have a question.
Professor, have a good one.
You too. Who is that?
Ramon.
Ramon, yes. What's the question?
So I have on I-38 and I-39, I have two inputs there. I don't know if they're just like random floating numbers.
Okay, which group number is your spreadsheet?
Group 4 or group 1, sorry.
Group 1?
Yes.
1, right? Okay, I'm gonna get the spreadsheet that you have there, so you can troubleshoot, figure out what's going on. Here you go. This one, group 1, spreadsheet correction. What's going on here? Group 1. Let me correction, something wrong here. No, I'm going the wrong way here. I want the raw data. Lab raw data, that's what I want. Lab 4, copy, that's group 1. Okay, so here you go. We are going to plot I average and V1, okay? And then you got your plot, right, Ramon?
Yes.
Okay, and then you have to invert the axis. Let's see if I can get the axis inverted. This one's gonna be J. This one is gonna be J. This one is gonna be G. This one is gonna be G. Okay. Okay, so you inverted the axis, right, Ramon?
Yes.
Okay, so now let's get the trend line and the R square. Okay. Did you get 1998 as a slope?
I got 2009.5.
6,000?
No, 2009.5.
2009.5. What is 2000? Okay, it's very close, right? It's not It's not much different. And what's the percentage difference you're getting?
1.35.
Ah, okay, so you're good.
Yeah,
Why?
what I'm asking is if you scroll down,
Oh, yeah.
there's those two numbers on I-38 and I-30 and
Ah,
J30.
okay. Don't worry. Don't worry. It must be some junk that I
Okay,
didn't remove.
I just
Just
didn't want to miss
clear.
anything.
Yeah, that doesn't, just clear content. Here you go.
All right,
Oh,
sounds good. Yeah, that's the only thing that was like confusing me.
okay.
All right, thank you, Professor.
Welcome.
Excuse me. I have a question too about this same Excel sheet because I'm also in group one. I was wondering how we find the confidence level if the R square is 1.
How you find the
CL.
the
if the
CL?
R square is
How you
1.
find the CL? Okay. Okay. So you got here, the spreadsheet, how do you call it? The regression equation, right? Did you get the regression equation?
Yes.
Did you get which slope did you get?
1998.
1998. Okay, just like mine. And which R squared did you
Yes. 1.
Yeah. Okay, you gotta fix this one. Okay, you don't want the number 1 in there. You have to change this thing so it shows a number that's different of 1. Okay. So how do you do that? You click in this little box here. Do you see the box highlighted?
Yes.
Right. Okay. Right click, and then you highlight Format Trend Line Label. Highlight Format Trend Line Label. Okay. So in this category here, make sure you have this thing highlighted. In the category, instead of general, you highlight number. Okay. And then you put like 5 decimal places, maybe 6, okay, depending on your number that you're gonna get. And then look at your R square. Now, instead of displaying 1, it's displaying a number that's not 1, right? 0.99999, right? Okay, so that's the first thing. That's the first thing that you gotta do. Okay, make sense?
Yeah, it just didn't change on my Excel sheet.
It didn't change on yours?
No, we just added a bunch of zeros after the 1.
Okay, so there's another way. There's another way of doing the same thing. Okay, so let's do that. Now, so this one is a little bit more complicated, but you're gonna be able to highlight one of the cells, one of the blank cells. Okay, and type equal. Do you see equal there? RSQ for R square. RSQ stands for R square. It's a function in Excel. Okay. Open parentheses, non-Y values. Then you have to highlight the Y values. The Y values in this case is those values here for V1. See that? Comma. And then you have non-X values. Highlight, click and drag. And now it's going to provide you with the value of the R square. Okay, see that? 0.9999869. Okay?
Okay, yeah, I got it now. Thank you.
2 different ways of doing the same thing. If this one here doesn't work, then you have this backup. And okay, and now you still have to know how to write down the CL, right? Right?
Yeah.
Okay, do you know how to get the CL?
Yes, I do. I look on the
Huh?
the PDF that's on Canvas.
Yeah, that's right. The PDF, you put the N value here, right? It's gonna be 10. The equation, the value of R squared, and then from the N and R squared, you can get the CL. Okay?
Okay, thank you.
Welcome.
Professor, I had a question for lab 3. You know how we were doing for the first graph for table 4-1. You know how you said that to put the significant figures, if it's 1, to add like 7 of them?
Yeah.
Well, mine didn't, so I added 8, and now I'm like confused with the CL because when I was looking at the chart that you gave us, it exceeds the CL that you gave us. So how am I supposed to do that?
Okay, so you're talking about lab number 3, right?
Yeah.
Okay. Okay, so let's go here. I'm gonna get the table, the CL table. You got what, 10 to minus 8? Is that what you're telling me?
Yeah, because I couldn't get the 10 minus 7, what you said last 2 weeks ago, so I added one more, and it gave me like almost 1, 2, 3, 4, 5, 6, like 7 nines, and then the last number is 6.
Yeah. Okay. The situation is the following. I understand what you mean. Okay. Let's download this thing here first. Right. Okay. Your table, it goes only until 10 to minus 7, right? You see here?
Yeah.
It doesn't have 10 to minus 8. Right?
Yeah.
So in certain cases, your R square is going to be to the right of the most extreme R square, right? Your R square is going to fall outside the table, right? That's what's happening to you.
Yeah.
Okay. So when you have something like that, what do? You write down 1 minus 10 to minus 7 as the CL lower bound, the lower bound of the CL. Okay. Make sense?
Yeah.
Lower bound. Now the question now is, what about the upper bound? Okay.
Yeah, that's.
You cannot say that's 10 to minus 8. You cannot say, because the table doesn't display those values for you. Okay.
Yeah.
But you can certainly say that it's going to be less than 1. It's going to be greater than this value, but it's going to be less than 1. Because why is that? Because this alpha value and your CL value are values from 0 to 1. Okay. In the extreme left, CL is going to be 0. In the extreme right, the CL is going to be 1. Okay? So don't put 10 to 1 minus 10 to minus 8. Put just the number 1 there.
Okay.
Now, and 1 means what? 1 means 100% confidence level. That's what 1 means.
Okay. And then and then I only have the other question for, I think it was the third graph, which was table 4-3. I got my R squared. Well, my last graph actually, table 4-4. I got 1 for my R squared.
Oh yeah, that's the same thing that the other student were having a problem, right? I forgot her name. Okay, so you have just like here, right? If you do not have, enough decimal place, see here? If you do not have enough decimal places, you're going to get the number 1, right? I'm gonna plot this graph again, right? So let's see. Here you go. I don't even need to plot the graph again. All I have to do is to add the trend line, right? Display equation chart, display R square, right?
Yeah.
Okay, here you go. Just like you, right? You're getting R square equal to 1, right?
Yes.
Okay, so how do we fix that? There's a way to fix that. Okay, click this box. There are actually 2 ways of fixing that, okay? Click the box, right click, and then go to format trend line label. We want to format this trend line label. That's what we want to do. The trend line label doesn't have enough decimal places there. That's why the R square is displaying as 1. R square will never be equal to 1, okay? So here goes. So we have to display it with more decimal places. Okay, so now I have this pane here on the right side, right? Make sure that the bars are highlighted and go to number category, highlight number, okay? Now we have 2 decimal places here, right? But the number is still 1. The number is still 1, so you do not have enough decimal places. So what we have to do? We have to increase the number of decimal places. Let's see, if we increase to 3, do you get a number different of 1? Not yet. 1.000, right? It's just a matter of finding out how many decimal places the R squared turns out to be a number different of 1. See? 5 decimal
Okay.
places. Okay? 5 decimal places. That's one way.
Okay.
If that works for you, then you're good. If that
Yeah, it works for me.
okay. If that doesn't work for you, there's another way of fixing that. Okay. Okay.
Okay. I think that was all my questions.
Okay.
Thank you.
Okay.
Have a nice day.
You too.
Hi again.
Hello.
I just wanted to ask what happens if the R square isn't on the table?
Well, for which lab are you asking? Lab 4?
Yeah, lab 4.
Okay. So the R square is here, right? Do you see did you type the R
Yeah.
square there?
Yeah.
What value did you get for R square?
0.99998686.
Okay. How many nines? 4?
There are 4 9s
8, 6,
and
8.
8686.
Okay, good. So you did that, right?
Yeah.
So what's your question? You got the R square, and then what is that?
I don't find the confidence level when I pull
Oh,
up
the
the
confidence level.
PDF.
Okay, good. So
Yeah, because the max is 0.975 when the
Yeah.
n is 10.
Okay, there's a little trick there. Okay. Okay, that's the table, right? That's the table.
Yeah.
Okay, we are talking about 10 data points, right?
Yes.
Right in here, this rule. Your
Yeah.
R square is greater than this value, right?
Mm-hmm.
Okay, so your R square is actually falling outside your table in this blank space here. Okay? That's what's happening, your R square. Okay, when the R square falls outside your table, you have the following choice. You can come up and say, look, the lower bound of my CL is 1 minus 10 to minus 7. Okay? See that? Because my R squared is greater than this value. And the upper bound is going to be whatever number you have at the very extreme of this table that is not showing. Okay? Note, see what happened to those numbers. See, 0.95, 0.99, 0.999. Those numbers are approaching which value from the left to the right? At the very one, yeah. Okay, so the lower bound is going to be 1 minus 10 to minus 7, and the upper bound is going to be exactly 1. 1 and 1 is exactly 100%. Okay?
Okay. Yeah, thank you.
Okay. This is Benjamin. Thank you for letting me know.